Okay, so moving swiftly on, we will have next speaker. Timothy is here.
Timothy is here indeed.
Okay. Okay, so maybe we want to share your slides.
Yes, just a minute.
Thank you.
Not quite slides, but just a second.
Okay.
So,
very good. Okay, so
can you hear me? Can you see?
Yeah, I'm good. I'm good. I think that probably means that's okay.
Also, while I like giving hand sort of written talks, and while I'm writing, I don't see anything in the chat because I'm in my note-taking application and not in Zoom. So if anybody has questions, just sort of unmute yourselves and ask them.
Sure.
Please.
Yeah.
Okay.
Okay. So we're very happy to have Timothy Logvinenko from Cardiff, and I guess he's gonna present us the good old whiteboard, I guess, talk. And
Yes.
he's going to tell us about Heisenberg algebra and categorification. Okay, let's welcome him.
Thank you very much. It's sort of a pleasure to give a talk at this symposium. It's also a pleasure to have this. I mean, I will present results of very recent research of myself, Clemens Koppensteiner, and Adam Genge. And it is particularly sort of fitting because back in around about the year 2002, when I first met Young Hui, we were both PhD students, and we were both looking at sort of three-dimensional Mackay correspondence, myself from mathematical and him from sort of string theoretic point of view, and trying to find sort of deep meaning and material for future career in that. So I find it somewhat amusing that Young went on to work with John Mackay on sort of group theoretic stuff. So on sort of on mathematical aspects of this, while I was led by Mackay correspondence to a great deal of things, in particular to sort of studying Heisenberg algebras, which of course sort of come from physics and are deeply related to that. So also Young has prohibited me from using the word category in this talk. And this is very difficult when you're talking about categorification. So I'll try to use word category as little as possible in this talk. I hope Young will forgive me for mentioning it once or twice. So the origin, let me first sort of talk about Heisenberg algebra. I mean, it originates in quantum mechanics, which sort of looks at essentially, I believe, finite dimensional version of this. But the mathematical object you end up with is something that's called infinite dimensional Heisenberg algebra. So in a moment, I'll define it. My notation for it would be HK. K is not an index here. K is a sort of, throughout this whole talk, will be base field, assumed characteristic 0. And what this means, essentially, as you will also see in a moment, is not that I'm defining Heisenberg algebra over different fields, but rather that I'm defining it over a lattice which is born out of essentially considering field K as a point scheme. So in a sense, this is Heisenberg algebra over a single point. But this is all. This will all come later. For the moment, the generators, the ones sort of given traditionally, are, I mean, there is identity, and then you have this generators AN, where N lies in Z. And by convention, sort of A0 is the identity of the algebra. So relations, so you have a sort of K vector space generated by this basis, and the relations, there's sort of one Heisenberg relation. I mean, this algebra is almost commutative. Which is to say that the commutator of these guys is a delta function, but not between n and m, but between n and minus m. And then you multiply by m also. I mean, there is sort of scaling involved, which you could get rid of. So sometimes you would see just delta function here. So what this tells us is that sort of m commutes with an unless you have an and a minus n. And this sort of, the commutator there is identity. So to commute, commuting an past a minus n spits out this sort of extra identity factor. So the best way to think about this, if sort of the best concrete way to think about this, is we can think of this as, well, you know, I believe physicists would say free sort of rank 1 boson algebra. But this is really the ring of differential operators. Differential operators on the polynomial ring in infinite number of variables. Operators on a ring K, x1, x2, and so on, via the following identification. When you think about it, well, what's in the ring of differential operators in a polynomial ring? Well, you can multiply by x's, or you can differentiate with respect to that. And an for positive n. So I'm giving this definition for any positive n, is differentiation with respect to xn. And differentiation with respect, and the generator corresponding to negative number is multiplying by n times xn. So let me sort of mark this by dagger. And then you can see where the relations come from, because of course, if you sort of everything here commutes, x's commute with each other, but if you differentiation also sort of commutes, but if you sort of try to commute differentiation past sort of d by dxi past xj, then what you will get is sort of 0 unless you are differentiating with respect to the same variable, in which case you will get 1. So, and this automatically gives us not this way of looking at Heisenberg algebra gives us not only a useful sort of concrete example, which explains, in a sense, this relation, but also it gives us the Fock space representation. I mean, the ring of differential operators, by definition, acts on a polynomial ring. Fock space representation. Fk. This is just the polynomial ring. With HK acting via dagger. So n for positive n differentiate, and for negative n multiply by corresponding variable. And this representation is reducible. It's faithful. And it is of highest weight vector 1. Now, for what we do, and for what I will talk about in a moment, there is a sort of a slightly different presentation of HK, which is really just sort of combinatorial rescaling of the definition above. So let me mention that, because that is what we actually in geometrical situations end up working with. So this is alternative presentation of HK. So the generators are Pn and Qn for n greater than 0. And relations are that when you commute Qm past some Pn, what you get is the following. You get the sum from I equals 0 to minimum of Mn of all sort of essentially smaller powers than Nm of P and Q. This is sometimes called sort of symmetric powers of this operators. So, so QM is not just PM QM, it's also plus Pn minus 1 Qm minus 1 plus Pn minus 2 Qm minus 2, and so on until you're left with just sort of pure Q, depending on which of these guys is smaller. So when I say combinatorial rescaling, I mean, you can check that if you take the following generating function, you take Pn Zn. So if you organize these operators into this generating function, then that's the same. You can use this formula for turning one of this bunch of generators into the other. So this is exponentiating sum for m greater than 1, a minus m over m z to the power of m. And similarly, exactly the same formula for q's, only with am and not a minus m. Sorry. am over m z to the power of m. So we still sort of have sort of Pn's sort of correspond to a minus m. Qn sort of correspond to am, but it's a bit more complicated than that, and the Heisenberg commutation relation becomes a bit more complicated. So why would we want to bother with this presentation? One reason is that when in geometric applications, about which I'll come to talk in a moment. The other is that in these terms, the Fock space is just the quotient of algebra by the left ideal generated by all Q's. So Qn for all n is not 0. We don't want to allow 1 in our ideal, but everything else. And so this is sort of immediately very useful. You can see that it will be very useful for generalizing Heisenberg algebras, because at the moment we'll consider Heisenberg algebras about over something way more complicated than a point, and you wouldn't have this sort of very natural Fock space here, but you can always obtain Fock space by, as long as you sort of this bunch of generators generalize in a satisfying way, you always just quotient out your H by Q by ideal generated by Q generators. So I'm an algebraic geometer, slightly lapsed algebraic geometer. To do my algebraic geometry, I had to learn a lot of homological algebra and homotopy theory, but I'm interested in geometry. So the really sort of groundbreaking development happened in mid-90s, and it was due to Hirako Nakajima and Ian Granovsky, who both independently came up with the following story. So Nakajima, Granovsky. This was all happening in mid-90s. I was a first-year student in Cambridge when Ian's first paper on this came out. He was one of my lecturers, and I heard that he just did some incredible stuff on Heisenberg algebras. At the time, I didn't really know what they were, and I never expected that eventually I would write a new chapter in this story. But at the time, they both looked at the situation where X is a smooth projective surface. The great thing about surfaces is that you sort of have a very natural symmetric product of them. So you can consider Hilbert's scheme of endpoints, which is, it's something that parameterizes length and finite length subschemes of X. So roughly you take all n-tuples of points, as long as the points don't repeat. And that's what forms a big open subset of a Hilbert scheme. But then when points start repeating, what you do is you allow yourself to sort of take scheme theoretic fattenings. So it sort of take, instead of taking 3 copies of the same point, you allow yourself to take sort of third infinitesimal neighborhood of the same point. And that, so this is called Hilbert scheme of endpoints on X, considering this sort of length n neighborhoods of points in X. And this is actually a resolution of a sort of dumb symmetric product. This is a resolution of, and this fact is very unique to surfaces. So symmetric product of X is take ordinary Cartesian product of n copies of X and take a factor by the action of group Sn. What you'll get is a horribly singular scheme, because of course, the Sn has a stabilizer on any n-tuple of points where some points are repeated. So the moment you're sort of on one of these diagonals, you have stabilizers and your scheme is not likely to be smooth. However, this horribly singular thing has a nice smooth resolution given by a Hilbert scheme. This fails already in dimension 3. So, the Hilbert scheme of endpoints on X being smooth is the reason it is sort of specific to surface, and that is why this is smooth projective surfaces where this development happened. So here is a sort of theorem which wowed a lot of people at the time. By Nakajima and Granovsky independently. So if you take the Heisenberg algebra, but now not over a point, but over the cohomology ring of X. So there is a lattice version of the definition of Heisenberg algebra. If you have a lattice with a form on it, for example, a cohomology ring or a K-theory with Euler form. Then you can define exactly the same thing, but with P's and Q's are now indexed not only by these integers, which sort of tell you how they act, but they'll be also indexed by elements of your lattice. And then to commute Q past P, it's the same formula, but you insert here a coefficient which is based on the pairing that exists on your lattice between the elements which index Q and P. So this is the case where your lattice is Z. The pairing is the dumb one. The base, the one pairs with itself to one, therefore the formula actually tells you that what you must have here is a sort of I-symmetric power, the dimension of the I-symmetric power of the vector space whose dimension is the value of the pairing. Since the value of the pairing on Z is 1, and symmetric power of 1 will give you 1 here. And symmetric power of one-dimensional space is still one-dimensional, so all the coefficients here are 1. So in general, you will get a more complicated coefficients here, and they will depend on the pairing in your lattice between the elements which index Q and P. So Nakajima and Granovsky do not think in these terms. They think for example, Nakajima just took a basis of the homology ring, a basis which has a sort of nice geometric representation to it, and use that. So he just had operators in a Heisenberg algebra which were indexed by the elements of the basis. But in the lattice version, you could, if you have a basis, you can always reduce. There is a relation which reduces any Q indexed by some linear combination to the Q's or P's indexed by individual sort of basis elements of that. So roughly, once you sort of allow yourself instead of working over a point to work over sort of a lattice, and this lattice is always sort of cohomology or K-theory of a variety, and in case of the situation here is when your lattice is cohomology or K-theory of a point, which is just said. Right. So this slightly modified version of Heisenberg algebra. Notice, of course, if you fix a single element in the cohomology ring, then you just get the action of this Heisenberg algebra, provided it sort of pairs with itself to 1, of course. So this Heisenberg algebra acts on direct sum for all n greater than 0 of the cohomology rings of Hilbert schemes of endpoints on X. So the sort of motto was that Hilbert schemes of points on X provide the Fock space for the Heisenberg algebra indexed by for Heisenberg algebra over X. This is sort of Fock space representation, and it is like any Fock space representation, like Fock space representation should be. It is irreducible, faithful, and of highest weight vector 1. So basically, they did this. The construction was very geometric. What they did is they said, right, let's take a basis of cohomology, but suppose now each of the elements of this basis is represented by some closed subvariety. So in terms of sort of geometry of this subvarieties, they've defined cycles in the sort of products of the symmetric powers, which by the usual sort of, if you want map from cohomology ring of Xm to cohomology ring of Xm, you should have a cycle in Xm cross Xm. And these were defined in these geometric terms. This is why the result was so amazing. I mean, Heisenberg algebra, Nakajima's paper started by saying we describe a relation between two seemingly unrelated things, free rank 1 boson algebra and the sort of cohomology rings of Hilbert schemes of endpoints on a smooth projective surface. And it turns out that there are natural operators which act sort of on these cohomology rings, which satisfy the Heisenberg relations. But the whole geometricity of construction suggested it should lift from the level of cohomology to the level of actual varieties, closed subvarieties, which define those classes in cohomology. So this is where I sort of start breaking a little my word given to Young. So this should lift to the following level. So of course it should lift to K theory. This was in Granovsky's sort of original paper. So in fact, Ian sort of already on a level of, so this whole representation of Heisenberg algebra acts on rational cohomology, so cohomology ring. Now, in algebraic geometry, we like to work instead with what's called Grothendieck ring or K0 or K theory. So you can think of this as of a refinement of the algebraic part of the rational cohomology ring. Refines algebraic part. And now what is a Grothendieck ring? Well, what you do is you take isomorphism classes of sheaves, isomorphism classes of, vector bundles. On a smooth variety, you can just get away with vector bundles. In general, we have to use sheaves, which are sort of, if you have never heard of them before, think of what happens if you take a vector bundle, but then you sort of want to vary dimension of fiber over different points of your space. But you can just think of sort of, take isomorphism classes of subvarieties. I mean, sheaves is just sort of the way that you can most generally encode this information. And then for any short exact sequence, so when you have a subsheaf f of g, and then the quotient is another sheaf h, so, or sort of a vector bundle, or for sort of, or if you have subvarieties there. This imposes a relation that class of g in the Grothendieck ring is class of f plus class of h. So the point here is that we take all, if you've seen this stuff before in homological algebra, we take all non-trivial extensions, for example, G's extension of H by F, and we just kill the extension information. Anything that's an extension of two things is just their direct sum in the Grothendieck ring. So you don't need to know about any different ways of extending sort of H by F. So, and this is why you get a ring, because you forget all the information about maps between these subvarieties or sheaves and so on. And so if you want to work, I mean, anybody who looks at this construction asks, can we sort of do this on a level of subvarieties themselves? The moment you do that, you can no longer sort of forget the data of maps between the varieties. So you have to remember the data of what's called morphisms, and then you end up looking at derived category. So there is a sort of a more powerful invariant called derived category of X. So in this talk, it will be called dx. Derived category. So a sort of a ring is a bunch of elements in a sort of monoidal operation and identity. A category is a bunch of objects. A monoidal category is, for example, such as derived category of X, is a category, a bunch of objects, monoidal operations on them, but also a collection of, for any two objects, have a collection of maps between them. So this replaces the relation of two elements being equal is replaced by two elements being isomorphic, or just sort of non-invertible morphisms existing between them. And the objects there are complexes of sheaves. I mean, it's not enough to take just the sheaves themselves or subvarieties themselves, because in order to get something sensible, you need to do homological algebra, and homological algebra teaches us that never work with objects, work with complexes of objects. And if you've got a nasty object, replace it by complex of nice objects. So if your variety is smooth, you can work with complexes of vector bundles, because every sheaf can be resolved, every structure sheaf of a subvariety can be resolved by a vector bundle. Right. So, and this is a projection. There's a natural projection from derived category to K theory, and there is a sort of and the Holmes, the morphisms in derived category actually define you what's called Euler pairing on the Grothendieck ring, the one that's used in definition of Heisenberg algebra. So what we would like, sort of the immediate next question to ask, if in 1996 you've sort of looked at Nakajima's paper, is, do we have the following? Suppose, and derived categories have been around for a while, since sort of 50s, when they were invented by Grothendieck and Verdier. So if X is a smooth projective surface, sorry, can I just test that I'm still heard, because sometimes my Zoom freezes. Can I test that I'm still live?
Yep, it's
good
moving smoothly for me anyway.
Thank you so much. So X is a smooth projective surface. Do we have the action of the Heisenberg algebra indexed by its K theory? Let's move firmly into algebraic world. On derived categories of Hilbert schemes of endpoints for positive n. And when I say acts in this, each of those p, the way it works is each of those p, each operator pi defines a map from this direct sum to itself, which maps cohomology ring of any xn to xn plus I. And so, and Q maps cohomology ring of any xn to xn minus I. So sort of pi and qi go between these cohomology rings. So do these operators act by on derived categories of varieties? And actually, once you formulated your question like this, you can finally get rid of surfaces. And this was suggested in the sort of famous footnote 2 or 4, I think, in Granovsky's paper. So around about the same time, late 90s, we had this amazing sort of Bridgel, King, and Reed derived equivalence, which was put to amazing use by Mark Hyman. And this is, where me and Young come in, because we were both there in early 2000s. We were both looking at Bridgel, King, and Reed derived equivalence, which sort of was born out of Mackay correspondence and related the Crepant resolution of a quotient singularity in dimension 2 or 3 to the quotient stack, sort of equivariant derived category of the original space Cn, or the original Calabi-Yau manifold, if you wish. But Mark Hyman put it to a very good use on Hilbert schemes of surfaces. So this was the development in sort of the subject in early 2000s. And what it tells you is that if X is a smooth projective surface, then the derived category of the Hilbert scheme of endpoints is the same thing as derived category of SN equivariant objects. So, it's a derived category on nth Cartesian product of X. So this is SN equivariant derived category. What this means is that we take objects in the derived category of Xn, and then we add to them extra piece of data, which is how does each element of Sn act on them. So, equivariant category means sort of a category and with an extra, where to every object you also give an extra data which encodes the action. And this is pretty much by definition the derived category of n-symmetric quotient stack of X. So remember when I said that the nth quotient, so n-symmetric power of X, quotient of Xn by Sn is horridly singular. And the reason is because, you have this massive stabilizers where one points start repeating themselves in Xn. Well, it's been known for a while that, if you sort of want something smooth, you should remember those stabilizers. And then you deal with something called symmetric quotient stack. So smooth Dillon-Mumford stack, symmetric quotient stack, which sort of remembers just enough of group action to make it into a smooth geometric object, although sort of not a scheme. There's a whole field called stack theory. But from the beautiful thing about derived category, that from a point of derived category, you don't have to learn any stack theory. If you want to have a derived category of a space of a stack formed by an action on a space of a finite group, then you just take equivariant derived category of equivariant objects on UXN. So I lied a little. What I do is I take derived category of equivariant sheaves on Xn. So I take sheaves on Xn, vector bundles on Xn, which have Sn action, and then I take complexes of those. But somehow this is sort of smooth Dillon-Mumford stack. And this is what was sort of missing in order to generalize this to stack, to high dimensional varieties. Remember I said that we didn't have a sort of a smooth version of Hilbert, that this was a sort of a smooth geometric object which resolved all the nasty singularities of the quotient stack. Well, actually, you can just, as it turns out, it is just the same thing taking derived category of Hilbert scheme of points as taking derived category of this smooth stack. And then it's absolutely clear how to generalize this to any algebraic variety whatsoever. So ultimately, and that was sort of the footnote in Granovsky, although he talked about K-theory, not about derived categories at the time. So for any X smooth and proper variety, so for any sort of nice, compact, and smooth manifold, what we want is that the Heisenberg algebra defined by the K-theory lattice of X acts on derived categories of this sort of symmetric stacky powers of X. Actually, once you formulated it like this, it is not very difficult to define the functors which correspond to P and Q. Because back in here, the construction here was so natural. I mean, this is why this result was so admired. The closed subvarieties defining the cycles which defined action of the operators were so sort of, it was immediately clear what to do here. So it is easy using the same sort of geometric idea as in Nakajima and Granovsky. It is easy to define the functors. Right, it's now 12:30. However, I started a little bit late. How long do I have?
Probably another 5 minutes.
5 minutes. I'll try my best.
Yeah.
It is hard. It is easy to define the functors from derived categories sort of n symmetric power of x. It is easy enough to define any sort of PI operator indexed by some object in K-theory, a sort of object in the category, really. And Q operator going backwards between sort of Sn plus Ix. So that comes for free. You essentially use the same correspondences in the Nakajima-Granovsky. Here, sort of A is an element in derived category of X, and therefore defines a class under the projection in K-theory of X. So the point is that then to check that you have this, you just need to check that these functors, these correspondences between these derived categories, satisfy Heisenberg relations. And what you find out is something that's sort of absolutely feature of everyday life in categorical methods in algebraic geometry, that Heisenberg relations only hold up to isomorphism. Heisenberg relations only hold up to isomorphism. And then once you're in this situation where something that represents PQ is only isomorphic, sort of PI, PJ is only isomorphic to PJ, PI. You can do two things. You can just forget about it. You can say, I've got a weak action. The relations, weak action means precisely that you've got an action in some algebra, and the relations in algebra only hold up to isomorphism. Or you could ask yourself, what, these isomorphisms, which sort of replace equalities in the Heisenberg relations, is there any structure in there? You could try to study the structure that exists sort of between relations between relations, if you wish. And this immediately leads us sort of to categorification, which has been a buzzword since early 2000s. So I will try to sort of explain it in 3 lines. The basic idea that if you've got any object, algebra, Lie algebra, or a group, I'll demonstrate it with sort of, in case of an algebra A. To categorify it, you replace it with a monoidal category A. I will sort of, again, if you don't know what a category is, I'll try my best to give you an impression of what is happening. What are we adding to this story? Monoidal category A. So what is this? What does an algebra consist of? Well, algebra consists of elements, set formed by elements of your algebra. You have multiplication operation. And, this, so in your category, a category consists of a set of objects. So elements of your algebra become objects of your category. And then your multiplication is the monoidal operation. Monoidal category means that we have a sort of associative binary operation on the set's object of your category. Usually it's written as a tensor product. But now you have something new that doesn't exist in your algebra. Morphisms. This maps between the objects. So basically categorification is like adding the data of maps between the elements of your algebra, adding sort of an extra level of data. And it's added in such a way that when you have an isomorphism, any 2 objects which are isomorphic actually correspond to the same element in the algebra. So if you define your algebra in terms of generators and relations, here your sort of, by definition, your relations will hold up to isomorphism. Sort of, you sort of take a skeleton of your category, you kill all isomorphisms when you project back to the algebra. And then to give an A module. What is an A module? You know, it's a vector space or abelian group. M plus a map from A to endomorphisms, you know, the data of how each element of A acts on them. And then you should give this. So a vector space or an abelian group becomes a category. Same thing as here, only without the monoidal operations, just essentially a set, if you wish. But now there are maps between the elements of this set. So you have a category and you have monoidal functor. From A to functors from M to M. So when you represent your categorification of your algebra, you have it act on a category by functors in that category to itself. And now I'll finish this talk by essentially, I wish I had more time. I could have told you a lot more. I mean, the really exciting thing with categorification is that you have to, for some well-known structure, such as Heisenberg algebra, you have to come up with the data of what these morphisms are. You have to define them. You have to come up with a calculus of morphisms, which produces all the relations in your algebra, essentially. And our sort of theorem with Adam and Clemens is that we can do this for Heisenberg algebra, and we can do it in a way which unites and extends all the previous results on this. So while I'm writing out names of my collaborators, I'll mention that the attempts to categorify Heisenberg algebra have been happening pretty much since they invented categorification. Khovanov has done this for the case of your variety X being a point. So then the Heisenberg algebra defined by lattice K-theory of a point is just the original Heisenberg algebra in the very beginning of this talk. And Khovanov came up with a graphical calculus which described this morphisms in the category defined by this algebra. And then Kautis and Likata did a special case of this when X is the Hilbert scheme of points, not even on every smooth projective surface, but on minimal resolution of an AD singularity, essentially Mackay correspondence again. So as I said, this whole subject owes a great debt to this field of Mackay correspondence, which me and Young were thinking about in early 2000s. So in our case, V, the base object, is a smooth and proper DG category. And I will not even start to sort of explain what it is. Let me just say that this is essentially what in modern algebraic geometry is known as the non-commutative algebraic variety. So every derived category of every algebraic variety has a unique, well, sufficiently nice algebraic variety, certainly smooth and proper one, has a unique DG enhancement of its derived category. So think of this as taking an algebraic variety, taking its derived category, and then generalizing it even further. The reason to work with main reason to work with DG categories, and I'm skipping what I could spend half an hour talking about, is that you can very naturally form n-symmetric power of a DG category. You could not do this to triangulated categories. So if you try to do this, if you try to pull this trick for abstract triangulated categories, you will fail. This is where sort of higher category theory comes in. So that's the statement of our result. There exists, first of all, Heisenberg. Indeed, our paper is called Heisenberg category of a category. For any smooth sort of improper DG category, we define Heisenberg category HV. And this is sort of monoidal, or indeed in full generality we work, and it's actually a two category. It's sort of like a monoidal category with several objects, DG. And then we have a faithful Fock space representation, Fock space representation. which is a functor from this HV to the n the functor categories of all symmetric products, basically of V. So just as before, this is exact. And I will sort of not write, but just mention that, well, I'll write just one thing, categorifying. So HV, if you project all the way down to K theory from this sort of categorical world, then you will get, well, almost get, there is slight subtlety here, the Heisenberg algebra defined by the lattice of V. And if you project from this Fock space down to K theory, what you would get is the Fock space of K0 of V. So there's sort of classical lattice theoretic Heisenberg category and Fock space. I'm sorry, I think I've run over the time a bit. And there is, if I had more time, I would have told you about the graphical calculus, which was the main difficulty working here. But you know, I'm out of time. So thank you for listening.
Okay, thank you. Any urgent quick question for Timothy?
Can I just ask one very quick question?
Okay, you want master?
Okay, so
Sure.
just very quick one. Thank you very much, Tim, for the nice talk, and thank you for reminding me how we grew up together in parallel. Just a quick question on your the generating functions for P and Q. You've written in this very suggestive form, which looks like a local zeta function. Is there a story to that? Is it possible?
There may well be. I should think about this. I mean, in fact, no, I haven't marked, to be quite honest, we work mostly with this presentation. I have not sort of worked with these guys. I know that these formulas work and they give the rescaling. I haven't yet played around with them carefully. Our next project is essentially categorifying Virasoro operators, which requires me to learn about vertex algebras a lot more than I do know about them now. And I suspect that I'll be able to answer your question a bit better.
Sure. It's just that it looks like a really nice non-commutative generalization of a local zeta function for some variety. But
cool. I will think about this. Thank you. This is a very nice remark.
Thank you.
Okay, so if no further question, let's thank Timothy again. Yeah.